So this is a talk about Rust, and this is a talk about advanced Rust programming techniques. And the question I have is, who here is coding Rust? Actually, not even half of the room. Who here is coding Rust professionally? Not that many. OK. So this is actually a bit of an interesting part in this talk. Rust is almost 10 years old, so we can talk about advanced Rust. However, the question is what advanced is. And that is a frequently moving target. Before I start, just quickly about me. Hi, I'm Florian. You've seen that on the main badge. I'm the managing director of Ferrous Systems. I've previously been in the Rust community and the core team. I'm one of the co-founders of the Rust Foundation. I don't hold any of these positions anymore. Currently, I'm only the managing director of FS. So Ferrous Systems is a company that we formed in 2018, was the first company to be formed around Rust. And nowadays, we are actually a tool provider around the programming language. We have started out as a consultancy. It's been a pretty interesting trip, particularly with that pandemic in between, which gives quite a non-normal organizational development. However, we do maintain important things, particularly if you're using Rust Analyzer, for example, or like the Rust IDE that is produced by us. Enough about that. So what is Rust? There's the old definition from 2015, which is Rust is a systems programming language that runs blazingly fast, prevents nearly all seg faults, and guarantees thread safety. There's a very technical definition, for which reason it was actually changed in 2018 as a language empowering everyone to build reliable and efficient software. And I'd like to focus on these two things, particularly the reliable in this talk. And that means we're going to have a look at some of the things that the language gives us, but maybe from a little bit of a different angle. Particularly, we're not going to talk that much about memory safety, but rather about other things, how Rust manages problems. Memory safety has been like probably the thing how Rust entered the market, but there's way more beyond that. I've already addressed this, so the current challenge is how do I make this talk accessible to a wide audience, even though it's an advanced talk, and I hope I'll manage that, and I'd particularly later like to hear from the people who have not been exposed that much to Rust on how successful that was. So it's a talk about pretty basic stuff, but what is even basic about Rust is something that we're trying to currently start a conversation about. Everyone has heard about ownership, everyone has heard about borrowing, but there are also less spoken about topics. Particularly, Rust is a strong encapsulation language. It is important. It is a language that can hide bits of the program that are hard to manage, like, for example, mutability and unsafety behind that encapsulation boundaries. And I would like to talk a little bit about how that goes. So this talk is roughly split in two between perspectives on ownership and borrowing and the whole bit around encapsulation and immutability. Things I'll skip. Rust has an async sublanguage that is super interesting, but not part of this talk. It does generics like Java or C++, not something I'm going to linger too much on. Anything that has to do with foreign function interfaces, interfacing with C, and particularly, this is not a talk about type system tricks. As in every language with a static type system, there's a ton of these, pretty often also useful in the niche where they're useful, but you'll figure that out when you get there. So what problems does Rust tackle? Mozilla research, when they came up with Rust, found that in the complexity of their code base, which is their main code base, Firefox, 21 million lines of code, billions of deployments, all of their problems become very hard to tackle, particularly crashes and security bugs. And a lot of the bugs they introduce in their code base are actually not local, in the sense of you look at a function, you say, here's the bug. It's much more how components interact with each other is leading to problems, and particularly not necessarily while they're being built or while two components are being built, but actually while they move against each other. So this one gets evolved, this one gets evolved. Accidentally, you introduce a bug. This is often called action at distance. You change something over here, and it breaks over there. It was an explicit design goal of the Rust language to tackle these. So what did they come up with? Interestingly, if you look at Rust, and you look at the manual and the documentation, it looks like a very, very complex language. It has tons of small detailed features. It has traits. It has associated types and all of these things. And there's a lot of names for a lot of concepts in the language. But ultimately, what it boils down to is a language that deals with two main constructs. Data, particularly data structures, of which there are two in the language. Structures, like things with multiple fields, and enums, which represent alternatives, something that I'm not going to focus on a lot in this talk. And functions are the main way on how my program works. This is how I assemble it. Everything in Rust is a function call. We don't do casts. We have function calls, functions that convert one data type into another. And particularly everything where two components, and this is what I'm going to talk a bit about, talk to each other, like say I'm passing data from one thread to another. All of that is done through function calls. Rust, in that sense, is a lot more C-like than people would imagine. Particularly, it has nothing like classes. It has no inheritance. It has no automatic virtual dispatch. There's a virtual dispatch feature that you can work for, but there's nothing in the language that activates it just by you doing a certain thing. That means we're going to read function signatures a lot in this talk. Okay, to quickly reiterate. So Rust has two important basic concepts, and the first one is a thing called ownership. And it's a pretty radical approach to how data in a program is managed. Every value in Rust has exactly one unique owner. That means you introduce it, and you're allowed to do everything with it because you're owning it. You're allowed to mutate it. You're allowed to destroy it. And the thing you can do with it is mostly you can pass it on to other parts of the system, actually by doing a function call. So here's the function called takes ownership, takes a point, gives away ownership of that data. And if ownership is lost or given up in some shape or form, the value is dropped and cleaned up, usually deallocated. So this is a piece of Rust code that does that. The most important thing here is I've implemented the drop trait, which is a way to actually hook into that destruction function. And here's a very simple program that just constructs this piece of data, prints out debug output, which immediately prints that. And the important thing is this last line. When I implicitly let this thing fall out of scope, it gets destructed. But the important question here is, if Rust manages things to ownership, what can I own? And this is where it gets interesting. Rust works a lot by modeling through what do I even own. The simplest thing is plain old data, numbers in memory. It's me fine. A heap allocation, for example, a vector that allocates a piece of memory and allows me to read and write to certain bits of it. I can have data with additional lifecycle requirements, for example, a file pointer, or even just things as ephemeral as the privilege to write into, for example, the data section of a mutex. So what do I own is one of the first questions that is often missed. So there's a huge difference whether I'm owning the first structure, which is a point of two numbers, or a file, which is also just a number. But it happens to be that this number gets acquired by calling the kernel and represents something which is an open file on the file system. From a programming language perspective, that's actually similar, but they have vastly different handling requirements. In particular, if we look at the file, what we're looking at is a value that enters the program, gets used in some way, passed on, and when you drop it, it gets cleaned up, which in the case of a file means it is closed. And so Rust ownership is about resource handling, and one of those resources may be memory. It's often attributed to being a feature that is there for memory safety, but it's actually for resource safety. And that comes with an interesting repercussion. I've been talking at the beginning that I would like to talk about encapsulation. That means that in Rust, it is incredibly important that I cannot see what is inside of such a managed resource. It is very, very often, this is actually the documentation for the file structure, that the documentation even alludes that this data structure has internal fields. And that is important because that means that I cannot access them, I cannot manipulate them, and I cannot interfere with that lifecycle management that Rust has introduced. Because what I'm doing, if I'm owning that file, is I'm not owning a number. I am owning a resource that got acquired from the kernel that I need to properly handle and later close. So another interesting repercussion of that is that Rust's file has no close method. The way to close it is actually to throw it away. So I'm hooking into that simplistic lifecycle management, which I really want to reuse later. Okay. So what standard FS file really is a tiny state machine, a thing that we're going to exploit later. The second concept that Rust has, and in the beginning took a little bit of the limelight, although probably shouldn't, is Rust has references, similar to other programming languages. And that means values can be referenced. But in that case, there's a process going on which is called borrowing. What that means is, while a value is borrowed, the owner promises to not touch the data at all, particularly not remove it from memory, which means this reference can always be dereferenced. And two kinds of these references are available, which are the immutable and the mutable references. Similar to function here, instead of takes ownership, which had no sigils in its type signature at all, we have a function that's here that's called takes borrow, which takes a reference to a point data structure, as I have introduced earlier. And this allows these ones are allowed to be shared. So there can be more than 1, 2, 3, 4, 5 active at any time. They're immutable. And they have an interesting property. You cannot observe mutation through an immutable reference. This is where the advanced bit comes in. Very often, they are defined colloquially as immutable references do not allow you to mutate what's behind them. The guarantee is actually stronger. It is guaranteed that if you have an immutable reference, no one is allowed to manipulate what's behind them. And we have mutable references. Mutable references, as the annotation have ampersand mut instead of the ampersand. They allow manipulation of the reference data, but they are unique. So there can only ever be one at a time. And they cannot alias, so they cannot be pointed to the same memory location as other references, particularly not immutable ones. So it's mutable, XOR immutable. First of all, just quickly, how does a borrow violation look like? So I've been saying the owner is not allowed to remove data from memory while it's borrowed. This is a very classic Rust example. So I have my data that I had before, just a stand-in value. I reference that by using the ampersand sigil here. So I have a reference to data. I would like to print it out. So I have this println, debug output. And I've introduced I've forcibly removed data from the program. Rust has a function called drop, which forces, like drop is usually implicit. If you want to have it explicit, you just call the drop function on data, which forces ownership to go away in that moment. And people are often confused on how Rust actually does that kind of tracking. And it may be helpful to know that what Rust leans into is something called region-based memory management. So all the compiler does, it draws regions where data is in memory, this case, it's very simple. So data is in memory from line 1 to line 3. And then it draws another region where it's borrowed. It's borrowed from line 2 to line 4. And then it checks whether the borrowing region is within the region where it's actually in memory. Here it isn't, at the red line, so that's a violation. An interesting thing about the borrow checking system of Rust is it's incredibly simplistic. Most of the problems we observe in training is that people think it does more than that. It really just draws those lines, and we're going to draw a couple of more of those lines later and exploit that. The way to fix it is just don't throw the data away. As simple as it may sound. So how long data stays in memory in Rust is completely governed by this ownership principle. The referencing is really just a small checker on top of it, whether all references are sound. They don't influence how long data is in memory at all. So, in summary, ownership gives full right to manipulate the data. Borrowing allows viewing the data, giving up the ability to destruct it. Mutable borrowing allows mutating the data, giving up the ability to share it. And also, just to spell it out, you cannot get a mutable borrow from a borrow. I need that statement later. But there's already a couple of perspectives on this. Even without going any deeper here, that means a function like this, modify string, &mute string, is inherently concurrency safe. By definition, interestingly, Rust's memory safety around concurrency that you may have heard about is entirely by definition. Because a mutable reference is not only unique in the sense of it points to this part of memory, but also in time. There can be no two of those available at any time. So when you're implementing that function, you can be completely sure that this reference is only available once, and you don't need to think about concurrency at all. You're the only one who currently has mutable access to that piece of memory. Do whatever you want. Similarly, I've already hinted at that. That also means when we take the other perspective on concurrency, if I have an immutable reference, as long as that reference exists, I can be sure that there's nothing happening behind that reference. So for example, I can just print out this number that I've been handed, then do an incredibly long computation, and then print out that number again, and I can be sure it is exactly the same, because that's the guarantee of this that I mentioned. Immutable references are not allowed to observe any kind of mutation. There's no changes allowed. I have a few functions just to illustrate how you can use these things competently. So all of these are called the same, write to file, because that's what they do. They take a string and they write it to a file. But they do it in very different fashions. The first one, for example, takes a file and a string owned. So, and then, well, does something behind the covers. We don't know after this function call how long these things will even live, because we've given up all of our opinions and all of our, we're not the owner anymore, we don't care. The second one is a little bit different. Passes in a file. We don't care how long it lives when it closed, but it passes in the data that we're writing to it as a borrow, which means we do care that this data remains in memory. We may want to remove it or reuse it later. And the last one is the hard version that actually keeps all of the control on our side and also makes sure that this file is not accessed by someone else, because we're passing in a mutable reference. So which one of those is the best? And this is actually a question I get quite a lot in training. And classic programming answer, it depends on what we want to do. There's really no good decision making on which one of those is better. It comes down to software architecture. So the first one, for example, if I rename that, call it, for example, something like submit write-up. Imagine I have a whole component of my program that manages writing things to disk, and orders those operations. It is useful if this component is pretty liberal, has wide ability to manage all the resources it gets passed by itself. While, for example, write to disk is a way in which I can say, okay, I'll keep my data around, I'll keep it immutable while I'm writing it to disk, but then I want to continue with my program. But I want to close the file and push it away. So all of these things are actually can actually be modeled by these 2 or 3 concepts. So the important thing here is ownership and borrowing are contracts. So ownership is a contract that forces the caller to give up its interests in the data passed and puts the callee in charge. And that means it is, if we think about software architecture, a tool for decoupling, and a very strong one. Borrowing, on the other hand, is a contract in which the caller gives the callee access to its own managed resources, but only under certain conditions, mutable, immutable, all of these kind of things. But that also means it's strongly coupling, because the caller gives promises to the callee to keep the data around, not mutate it, don't touch it, and all of those things. So ownership and borrowing actually have a pretty direct expression in software architecture. And if we're talking about the thing that a lot of people probably have experienced in Rust, when they're fighting with that borrowing system, what we find is nowadays they're actually fighting with their software architecture. Borrowing for very short length is very, very easy. The problem is, once you have a program that has multiple components running next to each other, be it threads or just like, for example, you have an I/O layer and you have an application layer, and these start expressing opinions on how they manage their memory and buffers, which essentially referencing is, you're going to run into problems very, very quick. So this is basically the difference between these 2 pictures. If I can use ownership to, for example, pass data that is relevant for a task between components back and forth, and that passing is complete, while if I borrow, I start expressing a lot of opinions about what the other component does. And that runs you into problems very quickly. So, stopping point in the middle. So, Rust, from my perspective, suffers from, we talk a lot about the mechanics on how resource management is being done, ownership and borrowing, and not a lot about the repercussions and how they also relate with encapsulation. We can, for example, use ownership, particularly between components, to make sure that those components don't know a lot about each other, because the only thing we're doing, for example, in that example where, hey, write this to disk, here's data, you own it, fire and forget, let's go. Like these kind of things are incredibly useful and less really talked about. When we're talking about encapsulation, what do we have to hide? And here's another interesting thing about Rust. It has 2 other important modeling concepts that are often also not talked about, particularly not in beginner talks. One of them is immutability, and the other one is unsafety, which I would like to introduce, particularly because they are not that much talked about in beginner talks. They often get the so sometimes people get the impression that they're escape hatches that you reach for if absolutely necessary, but they're actually core language features and really useful. And what I would like to do for the rest of the talk is talk you through how Rust models a mutex. Mutex is interesting because it is the runtime expression of a Rust feature, unique access. But something like the Rust compiler works completely statically, but in an actual concurrent situation where we have multiple threads working, trying to work on the same data location, we need some kind of runtime mechanic to actually moderate that. A compiler can't prove concurrent code correct that is happening while it's running on a processor. It is inherently stateful and concurrent. It is a hard safety boundary. Misusing a mutex introduces hard-to-track bugs, particularly, for example, keeping access to the data manipulated for too long and manipulating it past the time where I held a lock. And it is also one part where strong coupling for a change is actually very useful. So here's how a mutex is being used in Rust. I'll introduce a small data structure, which is a counter. The only thing that has is it has a number inside. I'm going to set this counter up with the value 0. Just call this data, and construct a mutex around it. The interesting thing about the mutex constructor, it takes ownership. So it takes the data away from the caller and says, OK, I own the data now because I'm the mutex, the part around it. This is actually crucial. So the lifetime of this counter is very, very short. It goes from line 1 to line 2, and then the mutex takes over. The mutex, on the other hand, lives for the whole rest of this program, even to the part where we print it. And then there's a very, very short moment where we're actually borrowing the mutex out, which is when we're calling the function mutate counter. Immutably. That's an important part here. So here's the manipulate counter function. Takes a mutex. Mutex is parameterized for the counter that is inside. And we can lock that one. Don't care about the unwrap here. That is widely considered an API mistake. Just use it like that. I don't want to go into detail why that is there. So I call counter.lock. And what I get back is something called a guard. And that guard, again, represents I'm holding that lock. So I get ownership of, OK, I currently have this mutex locked. And I can use this guard to extract a mutable reference, and then just add +1 to that. That's my counter. So to draw those again, so I have those green lines. The green lines are immutable borrows. So I have an immutable borrow, which is the borrow of the mutex. I have an immutable borrow that comes out of it, which is actually comes from the mutex guard. Little explanation of the signature here. This tick underscore in Rust means this is a data structure that cannot live without another one. Something that represents this mutex is locked cannot live without the mutex that it is locking. That's the place where a tight coupling is important. And now the red one, that's the actual mutable reference. So wait a second. I've just spent like 20 minutes to explain immutable references can't produce mutable references. How does that work? This is actually what's called inner mutability. It is possible for Rust to produce mutable access to immutable memory locations. Now, this comes back to the point, like, is this a hack? Is this an escape hatch? But let's retrace this. This makes a lot of sense up until now, like up until we violated the language guarantees. So what we have is we have borrowed access to mutex. And the good thing is it's immutable access. That means we cannot manipulate the mutex. That's actually what you want. You want to hand every party that deals with the mutex a way to look at it. But you don't want to give them the right to actually deconstruct it, destroy it, or something like that. We can call lock on it to register our interest for the data that is locked inside. And by doing that, we acquire a token representing this lock, which is the mutex guard. This also blocks the mutex from being removed from memory. And this token represents our unique access to our inner data and is allowed to produce a mutable reference. So what we've done is we built an immutable fort, so basically a wall around the data that's on the inside, and we're moderating who's got access. So the picture I'm usually using is we've got a wall and a door inside, and we need to make sure that everyone goes through the door, and there's only ever one person inside, or one thread. So what does a mutex do? Mutex has a pretty interesting life cycle. It is created and at some point destroyed. But while it is created, we can start spinning through this small state machine again. We can lock it. While we have it locked, we can access the inner data. Then we can unlock it, and someone else can lock it, unlock it. And we can model this with values. So we can actually go and say a mutex structure holds the data in the locking machinery. So if we create it, we initialize the mutex. If we drop it, we destroy the mutex and the data. And then we can have a co-structure to that, again, managed through ownership. If we acquire it, we have a lock if we manage to acquire it. And if we throw it away, we'll unlock it, on the other hand. So we can just design it as I've just stated. So we have two data structures here, the mutex. Inside is something called an unsafe cell, which is just a marker for the compiler. Hey, we manage the mutability of this memory location ourselves. Don't make any assumptions about it. And we have the mutex guard. And the only thing the mutex guard holds is a reference to the original mutex. So once we create it, the only thing we can do is actually reference it. But what we also add is one of those drop functions. And particularly what this drop function does, it unlocks the mutex again. So once we drop the mutex guard, the mutex gets unlocked. And there's a pretty simple set of functions we need to implement on top of this, which is the new function, which is a constructor. I've deleted the whole details. We acquire a mutex from the kernel and all of these kind of things. But particularly, we have this lock function in a synchronous mutex that is, for example, implemented on Linux. This sys.lock mutex function will block until it's actually our turn. So we can be guaranteed that once it returns, we are the thread that is currently allowed to access the data. So the moment we construct this mutex guard, you see the comment besides it, this guard is unique due to lock mutex. And then we have this function called borrowMut, which then gives us a mutable reference to the inside of data. It is bound. This is what these small markers, tick G, say. It is the reference being returned by this is bound to the guard. So we have mutex, guard, and then a reference that comes out of it. Now the question is, how do we implement that? So how does the compiler know that we successfully implemented a locking mechanism and can safely pass out a mutable reference that is definitely unique at the time of its active? It doesn't. That's what unsafety is there for. And this is why we have jobs. If compilers could prove a statement like this, we'd be out of jobs, to be honest. So Rust has an unsafe sublanguage. And that sublanguage has two components, unsafe functions and unsafe blocks. Unsafe functions are relatively easy. They are not, they might run into problems if you call them wrong, which is why they're marked unsafe and come with a documentation of how you call them right. There's not much more to say about them. Unsafe blocks, however, are often misunderstood in that Rust has a marker in code that says, here is where unsafety may happen. And contrary to popular belief, that does not switch any kind of language features off. It switches an additional set of 6 different features on, which are actually, which, if you misuse them, could actually break the language guarantees. We're going to use exactly one of them, which is dereferencing raw pointers. And the only thing we actually have to do here is we need to acquire a pointer to the inner side of that mutex and dereference it. It's happening through the star operator. So you have unsafe, star PTR, and pass out a mutable reference. The big question here is that comment on top of it, safety. Why is this a valid mutable reference? So what have we built? We have built in not that many lines of code, a data structure, mutex, that owns that inner data that we want to lock. We have, from the outside, an immutable reference towards that mutex. When we call lock, we get a co-structure that is inside of the mutex that knows the mutex is alive, and once it returns, it knows the mutex is locked and is locked to the owner of mutex guard. It has visibility on the inside of the mutex. That's where the encapsulation visibility part becomes important. So it can actually call this borrow mut function, can get a pointer to the inside and cast it to a reference, particularly knowing that all of the locking operations have worked, and we hopefully implemented the mutex correctly. So there's a very long argument here. And there's a very important takeaway here. I've actually marked here which language features are used inside this argument. There's a crucial mistake that people are making when they're dealing with unsafe, which is thinking the number of lines of unsafe code in Rust is in any way important. The question is, how much of an argument do I need to make sure that this small two-operation unsafe block is actually valid? I need to prove that I've upheld the referencing rules, and I need to prove that, well, my mutex is working correctly and all of these kind of things. So the problem with unsafety is that there's insufficient knowledge, to be honest, that unsafe in Rust is particularly something that needs to be encapsulated and that needs to be reviewed in scope of the mechanics that it happens in. So in this case, we have a code module that implements a mutex. Every time we change something in there, we need to review, or particularly in the unsafe bits, but also in the safe bits, we need to review whether all of these assumptions still hold, which means reduction, compartmentalization, all of these techniques are very, very important when dealing these kind of things. So encapsulating unsafety is the goal of Rust. And if you're looking, for example, at implementations of mutexes in the standard library or in other libraries, what you'll see is that modern mutexes will actually start reducing those concerns to very small code modules. So they get internally separated into the unsafe bits, and then a very broad safe interface around it. So all of these things do impact good software architecture in Rust. So it is actually a frequent criticism of the language that that unsafe exists. But Rust was never about removing unsafety from programming. It was always about managing unsafety. And that's why all of these facilities are there, and that's why the strong encapsulation facilities are there. So we've actually covered quite a few questions in this talk. So if you start coding Rust, or if you're already coding Rust, these are good questions to always ask yourself while you're implementing something, even during learning. Much more than just memory. The question is, what resources do I manage? What is their lifecycle? Rust has basic lifecycle management in it. How can I encode invariants that are not immediately apparent in data? What is the relationship between all the resources that I manage? How do I encapsulate them? How do I group them? Can I hide their internal management? Hiding them makes it really, really better for people that use my code to later safely reuse it. If unsafety is involved, which shoulders do I stand on? Like, for example, in this case, using a vetted mutex implementation like pthvets or something like that is really useful because it makes a lot of my argument a lot easier. What is my argument? Do I understand the situation correctly? And if yes, can I build a safe interface around it, hiding the unsafety, which is essentially what we've done in a very, very short amount of time. So ownership thinking in Rust is really, really important because it governs all of those life cycles. Rust is also extremely strict and wants those life cycles to be managed by its really vicious on violations. Borrowing is a harder contract than people might imagine. Pretty often, ownership is actually the better choice, particularly when we're talking between components. And I hope I made a good case where immutability and unsafety are actually important parts of the language, even if it's something that you're immediately exposed to, or actually very often. But highlighting those concerns actually makes them manageable and makes the development of such interfaces possible. The distinction in a mutex between these are the immutable parts, this is the safety machinery that you're not allowed to touch, and this is the inner part that you are allowed to touch, is a pretty powerful feature. Well, that's it. Thank you.